Alright, welcome back to our last unit that we are going to be looking at. So this is Unit D, or Unit 4. This is on chemical equilibrium, and then in a later part we're going to focus on acid-base systems, but also concentrating on mostly equilibrium. So of course we are going to have to go over what equilibrium is. So this week is going to look at what equilibrium is. We're going to look at how to calculate concentrations at equilibrium, and even before equilibrium is established. And then we're going to look at something called Le Chatelier's principles on equilibrium. So first of all, we're going to have to get into what equilibrium systems are. So of course, as we know, the amount of product formed in a chemical reaction is very important. We had an entire unit on Chem 20 known as stoichiometry based on that, and we've seen it in even electrochemical cells and even thermochemistry. We looked at how much products are being formed. So one of the things that we always assume is that reactions are quantitative, meaning that the limiting reagent determines the amount of product formed and the reaction goes to completion. Now, however, many reactions do not proceed to completion. So that means there's going to be a mixture of reactants and products present at the end of reaction, and this of course can be explained using the collision reaction theory. As we know, things actually need to collide in order to react, so as all the products are being consumed and there's not a lot of reactants left, it's very hard for those reactants to find each other, and then of course the products can also collide with each other and react as well. So what we end up getting is that these are reversible reactions, where reactants are reacting to form the products in a forward reaction, and of course the products can react to form reactants in the reverse reaction. So for example, have right here we can get a forward reaction, A plus B is producing C, or C can decompose and then produce A and B. So you will notice that in order to kind of show that both these processes can happen, we're going to have dynamic equilibrium, and we're going to use a double arrow. So I normally write it like this. You can see it like that as well. As long as you see a double arrow pointing in two directions, we know that equilibrium has been established. So for example, an example of equilibrium, so using that double arrow, we have the formation of hydrogen iodide gas. So hydrogen and iodine can react, they can collide to produce hydrogen iodide gas. That's in the forward reaction, so following the top arrow, or two hydrogen iodide molecules can react with each other. Then we go in the reverse direction to reform iodine and hydrogen in the decomposition. So we end up getting both reactions happening. So of course, in order for this to happen, obviously we need to have all the reactants and products kind of enclosed so they can constantly collide with each other. So that's why for an equilibrium to exist, we need to have a closed system with constant macroscopic observable properties. So that just means the temperature stays the same, the pressure stays the same, concentration stays the same. We don't see a change in color, and same thing, of course, the pH stays the same as well. So this is how we know that equilibrium is going to be established. So theoretically, equilibrium is the dynamic balance between the forward and the reverse process happening, and the keyword here is the same rate. So a system in equilibrium changes on a molecular level, but of course the macroscopic will stay the same. So this is why everything on the surface will look the same, but on the microscopic level, not so much. So of course, for something to be in a state of dynamic equilibrium, we have the rates of the forward and the reverse are equal, or they're at the same rate. The observable properties stay the same, so there's no changing of color, no changing of temperature, anything like that. And the system is closed at constant temperature. So of course, it's a chemical equilibrium. It involves several substances, the reactants and products of a chemical reaction. The forward and reverse reactions are happening at the same rate. So same one that we just kind of looked down here, that we're just going to look at, is that we can have two hydrogen iodide molecules conforming into H2 gas and I2 gas. Right, so this is an example of a chemical equilibrium. Now, what happens is that we can look at it like this. So there's a competition between collisions of reactants to form the products. So as we know, what is kind of happening right here, if we follow the forward reaction, we can have two of the hydrogen iodide molecules reacting. We get our transition state right here. And then of course it can form our products, or we can get two of these coming together, forming our transition state, and then forming our two hydrogen iodide molecules. So we kind of getting both reactions happening at once. So it just depends on when these molecules can actually collide with each other and all this. So that's kind of one example on equilibrium. Now we can see this as well in another example, and this is one kind of brought up. Now obviously we don't have the ability to kind of see this in our own here, but we can just use kind of the pages like this to kind of see. So this is another example of dinitrogen tetroxide decomposing into nitrogen dioxide. Now dinitrogen tetroxide, so this one right here, is colorless, whereas nitrogen dioxide is brown. It's a brown gas. And of course during this decomposition, heat needs to be applied as well. So this is just kind of showing you, kind of using colors and stuff like this, how it would happen is that if the colorless dinitrogen tetroxide gas is heated, it decomposes to produce nitrogen dioxide, which is a brown gas. So at equilibrium, the color will remain constant. So for example, if we have the nitrogen dioxide in a ice bath, it's just going to stay colorless. Now as the ice starts to melt and we start to heat it up a little bit, we'll notice a pale brown color being formed. And of course, if we heat it up, put it in boiling water where the temperature stays the same, we will get this brown gas being formed. And then of course you can adjust the colors based on the temperature. So this is why for equilibrium we need to have a constant temperature. Now we can also represent equilibrium in graphical analysis as well. We can graph concentration versus time, can be used to study equilibrium. Now equilibrium is attained when the concentrations of both the reactants and the products do not change anymore. So for example, in our first graph right here, concentration versus time, we will notice that we're still following that NO2 and N2O4, right? So as it starts heating up, right, we can tell the concentration of the nitrogen dioxide is increasing, and at some point it levels out and the concentration doesn't change. Now same thing, the dinitrogen tetroxide, as it's heated up, it starts decomposing, so the concentration starts decreasing and eventually it flattens out. And of course this line where two of these guys flatten out, this right here, this is when equilibrium is established, right? Oh, sorry. It's right here. Now, of course, there's another way you can graph this as well, and this is when we look at the rate of a reaction over time. We'll notice that now we're not going to learn how to calculate rate. This is more of a university level chemistry thing. But of course, equilibrium established, you'll notice when the rates of both reactions are the exact same, that's how we know equilibrium is established. And just kind of going back to what those graphs actually mean, and you'll notice with the rate and of course the concentration, initially the forward reaction or the decomposition of the dinitrogen tetroxide was the fastest initially when only the reactants are present. Of course, with reaction collision theory, if you put in all reactants, they're just going to collide with each other and just start reacting immediately. So as reactants are consumed, as there's less reactants, right, they start to slow down because those reactants colliding with each other doesn't happen at the same rate because there's less things to collide with. Now, same thing as well, so the rate of the reverse reaction is 0 starting off because there are no products being formed, but then as the reaction begins to speed up as products are being formed, and at some point the forward and the reverse reactions become equal, and this is when dynamic equilibrium is established. So that's just theoretically what is happening with equilibrium. Now, of course, we will look at ways to describe equilibrium and actually put some numbers in there as well. So one way to describe equilibrium, and this is, of course, if more products are going to be formed or more reactants are being formed, if the forward reaction progresses at a, not really at a faster rate, but if we are producing more products, or what we're left with, if we're more reactants at the end of reaction, more products at the end of reaction, we will need to describe equilibrium. So two methods that we're going to look at, one of them is percent reaction, and the last one is equilibrium constant, so big K with a little c. So for percent reaction, this compares the actual product yield at equilibrium with the maximum possible yield of the product. Another way to think about this one, it's almost the same as percent. It's the same as percent yield that you would have done in Chem 20 in the stoichiometry unit. And that's actually what the percent reaction is. If you know stoichiometrically you're supposed to get like 5 grams of material being produced, but you only get 2 grams being produced, well, you know there's a certain percent based on that. And of course, equilibrium constant we will get to shortly. So let's look at our percent reaction. So for percent reaction, it communicates the position of equilibrium, so just meaning how much product's being formed, which means it communicates the extent of the reaction. So the percent reaction can be written above the arrow in a chemical reaction. So for example, if we go back to one of the previous examples that we already done, where this is in equilibrium, if we wanted to, let's say, communicate that 78% of all the reactants reacted to produce HI, we just write the percentage above the arrow, right? Now, I'm just giving you this percentage. We will find a way to actually, solve this as long as we know how much is being produced. We use stoichiometry and stuff like that. But for these here, you're just going to see a number written above the arrow. Now, depending on what number is above the arrow, there's different ways we can describe equilibrium. So we can describe something as non-spontaneous, reactants are favored, products are favored, or quantitative. So for a non-spontaneous reaction, we basically get a negligible or 0% reaction. So what that means is that we get no products being formed whatsoever. So position equilibrium, it doesn't really exist. Now, for reactants favored, so this means that at the end of the reaction, or the way the equilibrium is, we're producing the reactants. There's more reactants left than we have products being formed. So if that's the case, our percent is going to be less than 50%. And how we'll see that, we'll see our equilibrium arrow with a percent less than 50% above the arrow. Now for our products being favored, so that means we're producing more, we're going to see a percent greater than 50%. So same thing, we'll see our arrow, percent greater than 50% above the arrow. And for a quantitative reaction, we're going to be a percent greater than or equal to 99.9%. So basically it is 100%. So this is the only time you're going to see a single arrow. So this is why when we done stoichiometry in the past, we always use a single arrow to communicate that the reaction went to 100%. So this is just how they're going to look specifically, like position equilibrium here. Our next few examples are just going to be looking at how we're actually going to be writing out the reactions and stuff like that. So for example, if you're given something like this, when oxalic acid is placed in water, it ionizes at 23%. Write the equilibrium expression for the ionization constant. So if you remember where oxalic acid, where it's in acids ionize. So we have HOOCCOOH. So if you want to use the Arrhenius theory or the modified Arrhenius theory for the ionization, you can. I'm going to use the modified Arrhenius theory. So if you remember, that's where they react with water to produce our hydronium and our anion, because we get that hydrogen leaving one or the other. Now from the question, it states that this ionizes at 23%. So we just write 23% above the arrow and boom, we have our reaction. Now you can easily write this one as well as just ionization with the Arrhenius theory, where you just have oxalic acid. You don't have that reaction with water, but it just produces H plus and then same thing, HOOCCOO minus. Now for the other ones, same thing, it's just kind of figuring out what the reaction is and then just kind of communicating what happens and writing it above the arrow, right? So neutralization of hydrochloric acid with calcium hydroxide is a quantitative reaction. So if that's the case, we got hydrochloric acid, HCl, reacts with calcium hydroxide. It's a quantitative reaction, so we use a single arrow. Now remember, neutralization is just a fancy double replacement reaction. So we're going to get 2 H2O plus Cl minus. And to balance, a 2 goes in front of there. So of course this one here is a single arrow. Now, I'm just going to pause the video and put the answers up in 3 seconds, so or you guys should pause this and see if you can get example 3 and 4. And hopefully for those you get something like this. So we don't have any numbers with them, but if we do follow the chart up above here like this, we can, if we know products or reactants are favored, we can easily communicate that. So from this one, the decomposition of hydrogen iodide gas favors the Ford reaction. So we should see above the arrow a percent greater than 50% from the decomposition reaction. And then of course the formation of ammonia, NH3 from its elements, is known to favor the formation of the reactants. So as we know, formation of the reactants, we're going to see a percent less than 50%. So we have our formation reaction here, and we should see a number above the arrow that's less than 50%. All right, so it could be 12%, 20%, 3%, who knows, right? But we just know that it favors the formation of the reactants. So that's how we communicate using our percent. Now, of course, you can calculate percent and stuff like that if you're given actual numbers of equilibrium concentrations, which we will kind of get into that once we get into the next method, or even when we get into acid and base. So the next one we're going to be looking at is something called the equilibrium constant. So the equilibrium constant is K with a subscript C. So what this one is, it is a mathematical relationship, so we will need to review our algebra skills for this one right here, and this involves the equilibrium concentrations of reactants and products, and this is going to yield the equilibrium law. So the law of equilibrium states that there is a constant ratio between concentrations of products and concentrations of reactants at equilibrium. So that means if we are given a reactant looks like this, so the molar coefficient of lowercase a with A being the compound, and we can have a general equilibrium like this. So the equilibrium law states that we have, the equilibrium law is the concentration of the products to a power over the reactants to another power. So the powers here, X and Y, are molar coefficients. So what we can get, we have concentration of C. If we have two products, we're going to multiply these together, and they are raised to their molar coefficient. So it's going to look something similar to this. Now these are multiplied together, so depending on our reaction, we can have a bunch of different things kind of going in there together. Now we do have a little description down here below. We have Kc, the equilibrium constant. All the capital letters are the concentrations, the molar concentration, so moles per liter, of the respective reactants and products, and the lowercase letters, so A, B, C, and D, are the stoichiometric coefficients in the balanced chemical equation. So this is going to be very important that you need to be able to start off with a balanced chemical equation first, and then of course rearranging it and putting it into the formula, which we're going to get into a bunch of different examples like this anyway. So a few things to kind of remember when we are doing this is that this is going to be constant at a given temperature. So the equilibrium constant will change at different temperatures. The equilibrium constant is normally stated as a numerical value, so we can ignore all units when we're putting it inside of our equation. And when we're evaluating the equilibrium constant, if you see anything that is a liquid or a solid, they are ignored. So we only deal with molar concentrations of aqueous solutions, so AQ, and gases. And when we're done evaluating stuff, if we see an equilibrium constant greater than 1, that means the forward reaction, or the products, are being favored, or the percent reaction is greater than 50%. If we see an equilibrium constant less than 1, this means the reverse reaction is favored, or the equilibrium or the percent reaction is less than 50%. But we are going to use these words here, so forward reaction favored or reverse reaction favored. So the smaller the equilibrium constant, the more the system favors the formation of the reactants, or we start getting into that negligible thing where it's hardly a reaction at all, like there's barely any products, and that means as well the bigger the value, the more forward the reaction is favored. So the equilibrium constant indicates the percent reaction of the reaction and not the rate. And of course, if the temperature is changed, the equilibrium constant will also change. So let's look at some of these here. And as you see here, the equilibrium constant will not change if the temperature is constant, and it will not change if the concentrations of the reactants or products are changed, if a catalyst is added, or pressure and volume will change. We'll look at this at a later date. And that'll be Le Chatelier's principles when we get to that at the end of the week. So all we're going to do right now is just look at actually putting in some of these things into the equilibrium law. So for example, we have the equilibrium law for the reaction of nitrogen monoxide gas with the oxygen to form nitrogen dioxide. So we have our reaction. So first thing we need to notice, gas, gas, gas. So because these are all gaseous, they can be put into our equilibrium law. And it's only solids and liquids we omit. So you had to remember, the equilibrium law is equal to the concentration of the products raised to a power over the concentration of the reactants raised to another power. So our products is NO2. So if we knew the concentration of NO2 gas, that is going to be in our numerator, and the molar coefficient goes up on top. Over, we have two products, or two reactants. So we're going to get NO gas down at the bottom, and concentration of O2 gas. And of course, the molar coefficients need to go in front, so the concentration of NO is going to be squared, and for oxygen, it's just 1. And that is it. That is writing it the equilibrium law. Now we don't have any numbers to actually put in, but that's fine. Let's move on to the next one. Now right away, we see solid and solid. So we omit solids from our equilibrium constant. So that means if we have our equilibrium constant is equal to products over reactants, our products, so we omit that altogether. So that means we're just left with CO2. If we knew the concentration of that, we can solve. Now the molar coefficient is 1, so we put a coefficient 1 up above, and of course over our reactants. Our reactants is a solid, so that is it. So the equilibrium law for this right here is just going to be the concentration of CO2, and that is it. Alright, so pause the video and see if you can get this one right here, but this is very similar to the other one where just pay attention to our liquids, right? So we omit those, but just see if you can get this one here. So the answer is going to go up in 3 seconds. Boom. And we get the equilibrium constant is the concentration of hydrogen gas squared because of the molar coefficient of 2 times the concentration of oxygen. And there's no power there whatsoever. So just a few more. Now this right here, there's actually going to be writing the equilibrium law and of course plugging in some values. So this right here, phosphorus pentachloride gas can be decomposed into phosphorus trichloride gas and chlorine gas. So write out the equilibrium law for this reaction. Of course, we will need to have our balanced chemical equation first, so try that one. And then we have, if there's concentrations there, plug everything in. So I actually want you guys to try this one on your own. So pause the video and see if you can get the reaction and of course put everything down here. And I'm going to put up the answers in 3 seconds. And when you're done, you should get something that looks like this. So we have our reaction here, the decomposition of phosphorus pentachloride gas into phosphorus trichloride and chlorine. So we write out our equilibrium law. There's products over reactants. So we have that. And then of course, when we plug in our values for chlorine gas, 0.014, phosphorus trichloride 0.014, and of course over our phosphorus pentachloride, 4.3 times 10 to the power negative 4, we get an answer of 0.46, which just tells us that the reactants are favored. And finally, example 5, one of the last ones. So same thing with this one right here. We have our balanced chemical equation already set up. Now we have concentrations at equilibrium of right here, and this question is asking that find the concentration of SO3 for the following reaction if the equilibrium constant is equal to 85 for this particular reaction. So of course you will need to kind of rearrange and solve. Now, same thing, I just want you guys to kind of try this one on your own. So pause it and see if you can set up the equation and solve it. And if not, I'll kind of go over it right now. So the equilibrium constant, we got SO3 squared over SO2 squared times O2. So I have this one, so of course we do need to rearrange and solve for SO3. So in order to do that, we're going to get this. Right, algebra, so in order to get rid of two of these down here, I need to multiply. Of course, when I multiply one side of the equation, I need to do the other one, and we get that. And then, of course, to get SO3, because this is squared, I'm going to need to take the square root of everything. And when we do that, we basically plug in our values. So we got 85.0, 0.500 squared, 0.500, almost ran out a little bit of space there, and we get, oops, and when we are done, we get concentration of SO3 is equal to 3.26 moles per liter. And that's how we do that one. So just remember, or try not to forget, that the SO2 was squared here, so that's why that square showed up there. All right, so that is, of course, using our equilibrium law and solving for some concentrations. All right, and last but not least, and that'll be the end of this lesson, is that so all these here we're dealing with the Ford reaction, but sometimes as well. So if the equilibrium constant, or Kc, for a reversible reactions, we had A plus B produce C plus D, we just call that one, just say K, right? The equilibrium constant. Now, if we looked at the equilibrium constant for the reverse reaction, basically all we need to do is just take the reciprocal. So the reverse reaction, in order for that one here, so Kc, this is normally Ford reaction. If we K prime C, that's normally reverse. So an example of this is how you can easily pull these off. If we look at something like this, so the decomposition of bromine monochloride is 11.1. So this is a decomposition right here. So Kc is equal to 11.1. That's it. Now, if we wanted to look at the formation of bromine monochloride, which is just the reverse right here, so if we want to go K prime C is equal to 1 over Kc, we go 1 over 11.1, and we get an answer that looks something like this. Now, it should make sense as well, is that if the decomposition, we have a number greater than 1, so the products are being favored, so that means these guys right here, so bromine and chlorine, are being favored, the formation of those are being favored. Whereas if we take the reverse reaction, right, or the formation, so we got bromine and chlorine react to produce bromine monochloride, we have the reactants are favored, so same thing, that means that these guys are being favored. So you'll notice that we're using the same numbers and everything like that, but whether we're looking at decomposition or the formation, they're telling us the same thing, is that bromine and chlorine are being favored in this particular reaction. So that is it for our equilibrium stuff, so, or Kc and the percent reaction. So in your workbooks, there should be some work on these here, so please give them a go. Check the answer keys up on Google Classroom and everything like that. And our next lesson is going to be on ice tables, so this is when we're really going to be looking at the mathematical implications of the equilibrium constant and stuff like that. So anyway, that'll be it for today, and see you guys for the next one on ice tables.